Yeah, I think it's easier to do it this way, right? This is also impossible because this is the same argument as the original Corning-Groves bridge problem. If you have two vertices of odd degree, then you have basically like 3 or more vertices which have to be starting and ending vertices, and you just can't have that. So then it just must be 2 by process of elimination.
Do you have to prove that it's like possible to have an Euler trail but no Euler circuit?
Well, not yet. So far, I'm just saying.
I mean, you can just have the first one.
So far, I'm just saying. Suppose there is one.
It could be back.
Right?
Yeah.
It could just be vacuously true.
Like, you've proven the ifs.
Wow. Good. Okay. The other direction is to say if there are exactly 2 vertices of odd degree, and then from this we would like to conclude that there actually is an Euler trail, but no circuit. And there's kind of a cute way to do this, which means I don't have to repeat the entire algorithm all over again. Anyone see what to do?
Start from one of the odd vertices. Prove you end up.
Wait, add the edge.
Yeah, so suppose that like V1 and V2 are my 2 vertices which have odd degree. And yet they are not connected. Wait,
It doesn't matter.
I guess it doesn't matter. Yeah, you can just add another one. So whether they're connected to each other or not, add another edge to V1 and V2. If I add another edge to V1 and V2, I've now made them all have even degree, all the vertices. And now by the previous theorem, there is an Euler circuit. And so to make it an Euler trail, just like take out that new fake edge that you just added. Bam. There you go.
Fake news.
Cool. What'd you say?
Fake news.
It's not fake. What? Okay, good. Good. All right, there's more. So that's any other questions about these things? All right, I feel like I know everything there is to know about these Euler trails and circuits. How about we're getting to that. How about the sort of analogous idea? Here we have been exploring the number of ways to go on a walk and use every edge exactly once. What if I want to use each vertex exactly once? Well, our friend William Rowan Hamilton, doer of many, many other things. This is, yes, if you took logic, this is the same guy who invented quaternions. This is the same guy who did the Hamiltonians, did lots of physics, lots of math. He was also a pioneering guy in graph theory. And he was also a budding businessman who attempted, I don't know if you guys read this in the book or not, he invented a game. And the game was called. So you might need to go. What's it called?
Over there.
No. What's that? Hand. What the hell is the word for that?
Handheld?
Handheld. Yeah.
No.
Okay. Good. So who would like to play the game?
I would.
Oh boy. Okay. Good. We'll do it all together. No, I don't know. Who cares? I don't care. Paper, scissors, rock with you two. Paper, scissors, rock.
You always go wrong.
Boom. All right. Good. Can you see? All right. So here's what we are doing. Everyone should gather around. It's like a drama.
Is this a local game?
It is.
Cool.
Wait, this is super zoomed in.
Is that good or bad?
I don't know.
Okay,
I
good.
can only see your hand.
Okay, good. This is a
Maybe zoom out a little.
dodecahedron.
I don't know how.
One of the. You can also like remove the thing from the thing. And then you put your hand in there. It's like more exciting. All right. Good. So we have this is a dodecahedron. It is one of the Platonic solids. It is composed of 12 regular pentagons. So that's pretty exciting. We're gonna have more to say about this like next class. Okay, here's the game. Considering the vertices of this polyhedron to be the vertices of like a graph, please find a. Wait, maybe I should have introduced these terms first. Whatever. A Hamiltonian. There are two things to consider. A Hamiltonian. Trying not to mess this up.
Cycle.
Hamilton cycle?
And the other one is a path. Yes. Okay, so a Hamiltonian path is merely a one in which vertices are not repeated. Is a Hamiltonian path, and a Hamiltonian cycle is one in which you use every vertex, and the only vertices which gets touched twice are the first and last one. Okay, so can Jamie do it? Let's start here. Is that an okay choice for you, seeing as that's a perfectly symmetrical figure? Okay, good. Which vertex would you like to visit next?
This one.
I think that was also an arbitrary choice. And so we can do a little coloring thing for the people at home. Okay, good. What next?
This one's awesome.
It's probably still arbitrary, yeah. So what do you want to do?
I guess this one.
Okay, he is now using up the vertices one at a time. Is everyone following this?
Follow.
Okay, good. Next.
No longer arbitrary.
I'm going to hand this to you in about a second.
This one.
Okay.
Decision fatigue.
Not decision.
Okay, good. The arrows are just so we can trace it later to see if like we're like going to say good job or this is where you screwed up. No, those are arrows. They're bad arrows. Okay, here you go.
Oh gosh. So I should arrow it as well.
Yeah.
I guess I'll go.
Is that coming out clearly?
It is.
And also the crowd can like help him maybe in theory. Yeah.
You got this.
Oh yeah.
Yeah, you got this.
Okay,
Woo!
so right now what I'm doing, I don't actually know anything, but like I'm just like making sure I don't use like all from the same pentagon. I don't know if that's the right move, but like, oh now, wait, what happened? Oh yeah,
Hamilton went around England trying to sell this as like a game. That's my understanding. I don't know too many details about this.
Why is it called the Icosahedron game?
What?
Why is it called the
Icosahedron
game?
This is the
So
Decker game.
I'm trying to make a.
So we did
Oh, yeah. I think you might have like almost. I think we might have some problems, right? Because
I might.
you can't. Well, I don't know.
Ooh, I'm kind of like splitting it in half. Maybe that's not good.
I feel like you've already lost. I don't think anyone's ever lost before.
I'm trying to make.
No, but then wait, then you can never get back down here, right?
I can't.
think did you already lose?
Yeah.
I thought you already lost.
I didn't actually think about what I was doing.
I think we need to back up, right?
That's okay. That's okay.
No, wait, should we back up too?
Sure.
Yeah.
Disaster.
So if we back up to, now do you have an idea?
Yeah. Let's just go to the top.
Yeah, and then like take care of them all and then come back, swing back down.
Yeah. Oh,
Yeah.
actually, I think I have to go this way. For sure.
Yeah. Boom.
And then I have to go around.
Making their faces sad.
Why? Why sad? Okay, good. This is pretty riveting. Okay, wait, how's it going? All right.
A spectator sport.
Do we get the general gist? Okay, good. All right. You're invested. Oh, should we wait? I kind of lost concentration. Somebody, are you paying attention?
Yes.
What should he do next?
He has free will.
Wait, is he trying to make a trail or a path?
A path. No,
Where did I start?
God, why do I keep
Oh no.
Wait, I don't know where I
Trace
started.
the arrows.
Yeah, a path. A path. So a path is one in which we use. I mean, a path in general uses
I was
doesn't.
only trying to make a path.
Yeah, path.
Oh, I thought I was trying to make a cycle.
Oh yeah.
No
So
path.
I was trying to be.
Cycle's impossible.
Oh.
I have no idea.
Okay. Well, yeah, I definitely made a path, but I thought I was
Oh,
trying
good.
to make a cycle. So I was
No,
trying
just
to
a
make
path. Path. Yeah, path.
Yeah, I made a path.
A path in general is a walk in which you don't reuse vertices. A Hamiltonian path is one in which you use all the vertices. Good. Okay, good. Hold on. Let me hold on to that for a second.
Oh.
I got a new challenge.
Can you ride a Hamiltonian cycle?
Does that mark? Can you check if that purple marker works well? All right. Good. That works very well. All right. Alice has the purple. She is Team Junior. Woo! They have this icosahedron, which is another platonic solid with precisely 20 equilateral triangles. Please mark clearly the initial vertex with the little arrow that you are using and do all the same thing we were just doing. Team Senior, I'll take this, is going to do the same thing with that marker, and we will race. Go! Path or cycle? Path.
Okay.
This is high drama here.
Are we making a path or a cycle?
Oh, I
Path.
a little arrow on the starting vertex.
Oh my God, we're losing time. We're losing time. I can't even see the thing.
Losing time.
All right, this is fun. All right.
Alright, Meng, you wanna like criticize her?
Is Alice pretty much just doing it herself?
Yeah.
That's what I would do if I was on a team with Alice. I would just back off and let her make all the important decisions.
Oh shit, no.
Uh-oh. I'm not sure backtracks are allowed.
Oh. Well, it just happened.
Just
so
keep going.
It's okay.
Alright, Alice.
Last one, done.
Oh, the seniors win.
An extra year of
Exactly. All right. Cool. All right, give me this, please. Cap. Oh, terrible. All right. Good. That was our fake fun for today. Fake fun. You know, it's kind of real fun.
I don't know why Hamilton wasn't
Class continues. All right. So I should probably like write down what these things are because I neglected to do so before. Like I was saying, also there's half the people seem to call it Hamilton, like Gossett, and half the people seem to call it Hamiltonian, which sounds more like English to me. So a Hamiltonian path is a path, which means no vertices are repeated, and Hamiltonian in that every vertex is used. A Hamiltonian cycle is a cycle. A cycle is one in which you start at a vertex and you end at that same vertex, using no vertices twice except the first and the last. That's just the definition of cycle. A Hamiltonian cycle is one in which you use every vertex once. Or you use every vertex. Use every vertex. Are we good? Okay, so we would like to know when we have such things. And unfortunately, there's just like no simple theorem that like directly characterizes Hamiltonian cycles the way the other proof did in the backboard. But we do have some theorems which say if certain things hold, then we will for sure have a Hamiltonian cycle. So there's this big theorem in the book. I don't know if you guys looked at it. We're going to prove it right now. It's quite hard. I think it's like one of the hardest proofs of the year. Ready? Okay, good. You're like taking notes and paying attention and everything? All right. All right, so here we go. Let G be a simple graph with n greater than or equal to 3 vertices. Okay. Let delta be the minimum degree of a vertex in this graph, or so let delta be the degree of the vertex with minimum degree. Yes.
This is like very important because like the problem of telling whether a graph has a Hamiltonian cycle is like NP complete. If you know what that means.
I do know what that means.
Yeah.
It means it's really hard to do.
Yeah.
It means there just basically is no algorithm
Yeah.
that we know of that's like simple, which will tell you whether it has.
Quickly tell you whether it has.
Right. Yeah. So I don't think maybe I knew that. Maybe I didn't know that. But what he's saying is the general question of given a particular graph, does it have a Hamiltonian cycle, is very, very hard. Okay. So it would be nice, dude. It would be nice to be able to say that it has one given some other method versus just like blindly searching for it, because that's really, really, really difficult. Okay,
What's complete?
this is a whole nother thing.
I'll tell you something.
Yeah, I thought you guys all knew this kind of stuff already. Do you guys know P versus NP and all that stuff? Doesn't that come up in like
Yeah,
AOA?
but like there's a hard complete thing, which I don't think we
Okay, good. All right. So anyway, we move on. Let T be a simple graph with n greater equal to 3 vertices. Let delta be the degree of the vertex of the minimum degree. The claim is, so this is the theorem. If delta is greater than or equal to n over 2, then G has a Hamiltonian cycle. So the way I think of this is you have a graph. You want to be able to start at a single vertex and move all the way around the graph and end up back where you started. First of all, we can restrict our, well, why can we restrict our attention to simple graphs for the moment?
Just get rid of extra.
Yeah, if you have a graph with a lot of, if you have a graph which is not simple, then if the so-called underlying simple graph has a Hamiltonian cycle, then so must the actual graph have a Hamiltonian cycle, because you just ignore extraneous edges. And okay, so yeah, it's kind of like, I think of this as like rumor spreading, right? You have some, here's my example. You have some graph, maybe looks like this. Yeah, here we go. And so here we have 5 vertices. So what this says is, if this condition is met for this particular sort of fake graph I'm about to draw, then that would mean that everyone is friends with at least 2.5 people, which means that they're friends with 3 people. Okay? So every vertex has to have degree 3, so it's at least, or 3 or more. So if have I done this yet? No, and there we go. So this is a graph in which every vertex has degree at least. No, I screwed up, right?
Yeah.
This is a graph in which every vertex has degree at least half of the number of vertices in the graph. And is it clear that there just is a Hamiltonian cycle in this graph? Someone like to give me one? Ishan.
Can you mind labeling stuff? Wait, you don't like.
I'm gonna stop talking. Okay, where do you want to start?
5.
V5. Where should we go? 4. To 4.
2.
2. 3.
4. Oh, sorry.
Probably like 1 next.
Yeah.
That's the only one left. Yeah, boom, and then back to 5. Ta-da! That is the Hamiltonian cycle for this graph. So just like duh, the more edges you have, the more likely you're gonna have a Hamiltonian cycle, right? It is graphs with not that many edges that we have to like worry about if we're really hoping that there's a Hamiltonian cycle. And this goes all the way up to like if there's a complete graph, like take K5, then like it will surely have a Hamiltonian cycle. If everything is connected to everything else, then you can just go more or less arbitrarily, and then you just get back again where you started. Okay, so the way I think of this in terms of friends, because this unit is all about friends, if you have a graph, so you have some friendship network, there are n people. If everyone is friends with at least half of the people, then there are enough friendships to sustain a sort of rumor spreading all the way through and getting back to the original person. That's actually how I think of what a Hamiltonian cycle is. Someone starts, in this case the starting person was V5, but actually once you complete the cycle it's sort of irrelevant where it started. So let's just start at V1 because it makes it prettier. So let V1 be someone who's about to start a rumor or tell a secret. Can you construct a path in which each person gets told the secret from a previous person and then that secret ends up back with that person? Cool. And actually there's a famous, I'll show you. It's kind of cute. You turn the lights off for a second. There's a famous Norman Rockwell painting. Does anyone know what I'm talking about? Where there's like a bunch of old ladies and they're telling gossip, and then the gossip gets back to the original person who
Telling
told
gossip.
it.
Making a joke. Like gossip. Lots of gossip.
Stupid. Ha ha ha. Keith, that's fine. Oh, wow.
Yeah. So, yeah, this is this, I don't know when this is from, probably like 50s, 40s, 30s, I have actually no idea. But here's this lady and she's like, oh, did you hear what just happened? My husband did something really stupid and he's dumb. And then she tells him that this is like some kind of, I don't know what this is, like satire of small town life. I'm not really sure. Things happen, and it goes around and around and around and around. Each person hears it and then calls the new person, and then suddenly this guy's like tells him, what? That was me! And then he's all mad. He's like, ah! You told a secret about me you weren't supposed to tell anyone. Okay, classic Hamiltonian cycle. A rumor spreads through the small town in such a way that every single person hears the rumor and then it passes the rumor on until it gets back to the original person. Good? Every single person hears the rumor exactly once and then it gets back to the original person. So maybe, after all, it's a positive story because it means that there are a lot of friendships in this town. Because you have to have quite a lot of friends in order for this Hamiltonian cycle to exist. Okay.
Wait, you don't have to.
You don't have to, but if you do, then you have a Hamiltonian cycle. This is a sufficient, not a necessary condition. Okay. Woo! Alright. First thing I would like to do, before we even really start the proof per se, is to talk about connectedness. So, someone say something intelligent about connectedness and Hamiltonian cycles.
If a graph is not connected, you can't have a Hamiltonian cycle.
Yeah, that seems pretty good. so note, if G is not connected, then no Hamiltonian cycle, because it's just like dumb. You can't get to all vertices because some of them are not even reachable from each other. But so you might think, oh, we better put like that the graph is connected into our conditions. But no, in fact, connectedness is implied by this condition that delta b greater than or equal to n over 2. So I would now like to prove that small claim. So claim if delta is greater than or equal to n over 2. In other words, if everyone is truly friends with more than half of the people, or half or more of the people, then G must be connected.
Is G a multigraph?
No, G is a simple graph,
Oh,
as it says that right there. Yeah, so, okay, let's do it. Why must G be, this is a classic little graph theory proof, why must G be connected, and therefore I do not need to mention that condition separately in the statement of the theorem?
Just assume it's not connected, and then if it's not connected, it's
Okay,
gonna be
yeah,
groups.
good. Yeah, so actually, should we just let Jamie talk, or should we think for a minute? Let's all think for a minute. He already said something, so I'll repeat what he already said. Well, basically he's like, assume it's not connected. If it's not connected, there must be two components. Why is that impossible? G is connected. So we're supposing that delta is greater than n over 2. We're trying to show that G is connected. Jamie says suppose it's not, and then we're going to get a contradiction. So suppose G is not connected. All right, what next?
And split it into two components.
Yeah, two or more maybe, right? So if G is not connected, then we have at least, components, components C1 and C2, and possibly more even. For purposes of specificity, let's let the size of the component C1 be N1 and the size of the component C2 be N2. So let there be N1 vertices in C1 and N2 vertices in C2, and there might be other components as well.
So the minimum of N1 and N1 through Nn has to be less than or equal to N over 2.
Yeah, I guess that's one way. Say that one more time.
The minimum.
Oh,
Well, because C1 and G1 are like multiple, so. Oh yeah, sure. Yeah. Either one of N1 or N, like the smaller of N1 and N2 has to be less than or equal to N over 2. Because if neither of them were less than or equal to N over 2, they would add up to more than N over 2. Yeah.
Yeah. Wait. I think I followed all that logic. First, just like note that N1 plus N2 has to be definitely like less than or equal to N. Okay, and now what you're saying is take any like, what are you saying? Consider component 1.
Consider component 1. If N1 is greater than N over 2, then N2 is less than or equal to N over 2. Otherwise, N1 itself is less than or equal to N over 2.
Well, could be other components, so it's actually
No, it doesn't matter at all. Minimal. It's just true.
Wait, sorry, when are you using this fact?
Not yet.
Oh.
Like you have a rock,
Later.
but we just know
Oh, okay.
This is just literally addition of facts.
right? Because they're supplying that.
Okay.
Yeah.
All right. Before I write that down, keep talking. I want to see how this is going.
Okay, and then so take the one that has size less than or equal to N over 2. Take some vertex V1 in there. Since we know that given the parameters we set at maximum, its degree can be N over 2 minus 1. N over 2 minus 1 is strictly less than N over 2, and therefore that's a contradiction.
Yeah. Okay. So I guess there's a couple of, I'm going to do this in a sort of direct way. I think what you said is good too. I can't decide which is better, but this is the one. So anyway, so let V1 be a vertex in this component. What can I say about the degree of that vertex V1?
It's at most N1 minus 1.
Yeah, it has to be
Less than or equal to N1 minus 1.
less than or equal to N1 minus 1, because that's how it works, right? In your component, at most, this can be related to everything else. But then also, no, I guess is that what I want to say?
Yeah.
Yeah.
Yeah, that's fine.
Okay, and then the same thing is true over here, right? The degree of V2 also has to be less than or equal to N2 minus 1. But then this also has to be greater than or equal to N over 2. Yeah, this is actually a cool way to do it also. And this has to be greater than or equal to N over 2. And so you just like add those two equations or something, right? Yeah. So if you add those two inequalities, then you get N is less than or equal to the degree of V1 plus the degree of V2, which is indeed less than or equal to N1 plus N2 minus 2. But that's just crap, right? Because because N, then you have N plus 2 is less than or equal to N1 plus N2, which is in turn less than or equal to N. So that's like N plus 2 is less than or equal to N. That's like no way.
Wait.
Contradiction. Yeah, so by like a sort of devious sequence of inequality adding, and it also kind of just like sort of makes sense, right? Within each component, if you're friends with half of the total people, then there's just not enough for that to be possible. Okay, good. All of that was simply so that we could dispense with talking about connectedness. Or rather, you can say so that we didn't have to add it as another condition to the theorem. It just follows from the single condition that we have. All right, now we're ready to start the real proof. Are you ready?
Yeah.
Okay, so first take an arbitrary n greater than or equal to 3. And I am going to attempt to prove that if this condition holds, there must be a Hamiltonian cycle. So the big picture is, I'm going to consider all possible graphs with n degrees
With n.
that meet the condition.
Is that like a look of surprise?
Okay. So I now create a set. So let S sub n be the set of all graphs such that G is a simple graph, a simple graph with n vertices, and delta is greater than or equal to n over 2, and G has no Hamiltonian cycle. So I'll say all that one time. Consider for a particular n, consider the set of all graphs which meet the minimum condition. So everyone is friends with at least half the people, or the person with the least number of friends is still friends with at least half the people. And there's no Hamiltonian cycle. Okay, what would we like to show about this set?
No.
That it's empty, right? So what parentheses I'll just say we want to show that S sub n is empty. If we can show it's empty, then we'll show it's just simply impossible for a particular n to meet this condition and also to have no Hamiltonian cycle. Cool? Okay. All right. So now I have this sort of also, there are only a finite number of possible graphs given n vertices that you could have. So this is a finite set. So within this set, choose the graph with the most number of edges. All right, choose the graph in S sub n with the most number of edges. And call it G. Okay. All right. So what is G? G is some graph. You know, it has a vertex set, an edge set. It has this function thing which maps edges to unordered pairs of vertices. And here's what we list every single thing we know about this graph G. Well, G has n vertices. Duh. Also, each vertex has degree. Each vertex has degree greater than or equal to n over 2. Also, what else about G?
Has more.
It's connected by the lemma. Yeah, sure. So G is connected by previous arguments. Also, well, I'll just say it. G has no Hamiltonian cycle, because that's precisely how we constructed the set. And here comes the crucial thing Jamie just said.
It has more edges than anything else that's in that set.
Oh, it has more edges than anything in that set. Okay, so yeah, so any graph with more